Welcome to this explanation for the seasons. In this video we're going to look at the reason for the seasons. We'll be looking at the lengths of the day and the night at different locations on the surface of the Earth, the solstices and the equinoxes, and how that's related to our calendar. And then we'll have a look at how the sun and the stars appear to move across the sky from different locations on the surface of the Earth, and how this is related to the seasons. Now, in the scene before you, I have two views of the Earth and the Sun. At the top, I have what I call the Earth view, and in the lower left, the orbit view. Initially, I'd just like you to focus on the orbit view. In this view, I have the Earth and the Sun, and the orbit of the Earth about the Sun. You can see that the Earth is slowly rotating, and it completes one rotation in approximately 24 hours. If I speed up time, you can see the Earth in motion about the Sun. It takes approximately 365 days for the Earth to go once around the Sun. Now, the important property of the Earth that creates our seasons is the tilt of the Earth's axis. In the orbit view, you can see that the axis is tilted so that the equator of the Earth is inclined to the orbital plane. That tilt is approximately 23.5 degrees, and as the Earth moves about the Sun, that tilt remains reasonably fixed. Now, in the orbit view, I also have a little white arrow sitting between the Sun and the Earth. I want you to imagine that you're standing where that arrow is, and you're facing in the direction of the arrow. Then on your left will be the Sun, and on your right will be the Earth. And as the arrow follows the Earth about the Sun, the Earth will remain on the right and the Sun on the left. That gives us the Earth view at the top of the screen. So currently, the North Pole is tilted away from the Sun. But as the Earth orbits around the Sun, the axis remaining fixed in its direction, as you can see in the orbit view, from the arrow's point of view, the Earth view at the top, you can now see that the North Pole has swung around and is tilting towards the Sun. Now I'm going to add a few more features onto the surface of the Earth. There's a red ring, which is called the terminator. It distinguishes between day and night on the surface of the Earth. On the left side of the terminator, every point on the surface of the Earth can see the Sun, and so it's daytime. On the right side of the terminator, every point on the right side can't see the Sun. The Sun is below their horizon, and so it's nighttime. I've also depicted on the Earth's surface a series of purple domes. If you look at the dome sitting at the North Pole, you see that during one Earth rotation, the dome is always in daylight. It has 24 hours light. It never is rotated into the nighttime. The same with the next dome. As the Earth rotates, that dome gets very close to the terminator, but still remains on the day side, as does every point within the Arctic Circle. So that dome is also experiencing 24 hours day. The third dome does move into the nighttime for a few hours, but has a very long day. As we move from dome to dome going south, in the northern hemisphere, the days are longer than the nights. But as we cross the equator, the domes are experiencing shorter days and longer nights. Until we get to the second last dome, and it's experiencing 24 hours nighttime for each day, along with the dome sitting at the pole. So the days are long in the northern hemisphere, and the days are short in the southern hemisphere. This is going to create two extremes in climate. In the northern hemisphere, it's going to be warm. The Earth's surface can accumulate sunlight and warm the surface, and the nights are short for the surface to cool off. So the climate tends to be hot. It's northern hemisphere summertime. And in the southern hemisphere, the days are short and the nights are long, and the Earth has longer period to cool off, and so it tends to be cooler. And it's southern hemisphere wintertime. If we move 6 months into the future, in the orbit view, the axis has remained reasonably fixed in its orientation in space. Then now the North Pole is tilted away from the Sun, and the dome sitting at the North Pole is in permanent darkness, along with the next dome, heading south. Looking at the domes in the Northern Hemisphere, they now are experiencing short days and long nights. It's Northern Hemisphere wintertime. And in the Southern Hemisphere, the days are long and the nights are short. It's Southern Hemisphere summertime, with the dome sitting at the South Pole in permanent light. Now the seasons are very much related to our calendar. I'm going to put markers around the orbit of the Earth indicating the different months. With Southern Hemisphere summertime, Northern Hemisphere wintertime, the Earth in its orbit is sitting in December. The other extreme that we had a look at with the North Pole facing the Sun is now shining on the Northern Hemisphere, and it's Northern Hemisphere summertime. We're sitting in June. It's approximately the 21st of June. This is one of the solstices, where the Northern Hemisphere experiences its longest day, and the Southern Hemisphere its shortest day. As we move around the Sun, and the Earth's axis lines up with the terminator, you can see that every dome on the surface of the Earth now is experiencing equal amounts of day and night. 12 hours day, 12 hours night. This is one of the equinoxes, about September the 21st. As the Earth moves through into December, approximately December the 21st, the southern hemisphere is now experiencing longer days, and at its longest, it's a solstice once again. And the northern hemisphere is experiencing its shortest day. Moving to March 21st, the Earth's axis is lined up with the terminator, and once again the domes are experiencing 12 hours light and 12 hours dark. It's another equinox. Our calendar stays in tune with those markers, the equinoxes and the solstices. Moving around to the solstice again, around the 21st of June. Now I'm going to introduce a figure standing on the surface of the Earth. This figure is standing in Sydney, Australia. And as the Earth rotates, you can see how its orientation in space is changing. I've also drawn on a blue disk. The disk represents this figure's horizon. Everything above this disk, from the figure's point of view, is above its horizon, and it can see it in the sky. Everything below the disk is below this figure's horizon. Around the horizon I've drawn north, south, east and west. I'm going to introduce another view. I call this view the local view. It's the view from the point of view of the figure. As far as the figure is concerned, it's stationary, along with the surface of the Earth, the blue disk, and it's the sky that appears to be moving. You can see the sun rising and setting in the local view. Now in this orientation, we're in southern hemisphere wintertime. The sun is going to rise towards the northeast, and at noontime, when the sun is at its highest in the sky, it's low towards the north. It doesn't get very high, and the path across the sky is quite short, setting in the northwest. From this figure's point of view, the sun spends a long time underneath its horizon, and only a short time during the day. It's this figure's wintertime. The sun doesn't get very high, the intensity of the light isn't very strong, and so it's cool. Let's move to this figure's summertime. You can see in the local view the sun is starting to get higher and higher in the sky. And now it's taking a very different path, as seen by this figure in the local view. At noontime now, the sun is very high in the sky. The intensity of the light is quite strong. And as it moves across the sky, it takes a long path, setting towards now the southwest. The sun takes a shorter path during the night and rises towards the southeast. Now let's have a look at a figure standing in London. For this figure, the sun is taking a very long path underneath its horizon at night time. The sun is rising towards the southeast, and at noontime it's very low towards the south. The intensity of the light is not very strong, and it's going to be cool. And the days are short as well. So it's going to be this figure's winter time. If we move now to summer in London, moving through to June, then at noontime, the sun is going to be much higher in the sky. And the sun takes a very long path towards the horizon, setting in the northwest, skirting below the horizon for a few hours, to then rise once again in the northeast. The days are long, and the sun is high in the sky during noon. The intensity of the light is stronger than in winter, and so it's going to be warmer. Let's now look at the North Pole. At the North Pole, it's 24 hours light in a day. The sun appears to be taking an almost horizontal path around the sky during the day. For the sun to start setting, we need to move towards an equinox. So about September the 21st, the sun is beginning to set, and it will take a few Earth's rotations for the sun to set. It's a very long sunset. And then for the next 6 months, the sun will be below that figure's horizon. Moving to a solstice. And the figure will be experiencing 24 hours night in each day. The stars appear to be taking a horizontal path around the horizon. None of the stars rise or set. And the stars the figure sees overhead are the stars it will see throughout the whole year. It never gets to see the stars below its horizon. The opposite, of course, is for someone at the South Pole. They see the opposite groups of stars. And the sun will be taking a horizontal path during the day. Now, of course, the figure won't be seeing stars during the day, but the stars that are overhead for that figure are the stars that will remain overhead throughout the whole year. Now let's have a look at a figure on the equator. For this figure, all the stars are rising towards the east and setting towards the west. All the stars rise and set. And it's only a figure on the equator that gets to see all the stars throughout the year. The sun is always in a position which is overhead at noontime. And there isn't a great extremes in climate throughout the year. And so the seasons are not so extreme on the equator as in other locations like Sydney or London. This is where I'll conclude my explanation for the seasons. In other videos, I give more detail about the relationship between the seasons and the calendar, a video on precession, the different types of days, and also a video on twilight. You can find the links below.